Hello everyone, I'm going to talk about posits, which is a new exciting representation for reals in computer systems, and how you can detect and debug numerical errors in posit applications using our approach. Posits are recently proposed by John Gustafsson as a drop-in replacement for floating point. Posits can provide more accuracy and dynamic range for the same number of bits in comparison to floating point. One of the cool properties of posits is tapered precision. That is, based on the range of the number of precision bits changes. IEEE floating point provides fixed number of precision bits for all normal numbers, whereas posits provide more number of precision bits for numbers near 1, and number of precision bits reduces as we go further away from 1. Another cool thing about posits is it can approximate sigmoid function efficiently. Sigmoid function is widely used in machine learning and it is computationally expensive. With posits with the right configuration, the sigmoid function can be approximated with few bitwise operations. This has created a lot of excitement in ML community to use posits. In fact, Facebook recently had a number system which was based on posits. So there is a lot of excitement to use posits, and if I've done a good job till now, I hope you are excited too. And you want to use posits to approximate real computations in your programs. You're going to face numerical errors, and that's where we want to help with PositDebug. Let me give you one slide summary of my talk. PositDebug is a compiler instrumentation framework that performs shadow execution with reals to detect numerical errors in posit applications. PositDebug can detect all numerical errors, including cancellation and branch flips, which you might have seen with floating point, and some more which are amplified by posits. Our goal was to run PositDebug with long-running applications efficiently. The idea behind PositDebug is to store constant amount of metadata with each memory location and still provide the directed acyclic graph of instructions for root cause analysis. The smart design of metadata makes PositDebug scalable with long-running applications. While building PositDebug, we realized the same ideas can be applied in the context of floating point. We built a floating point version which we call FPSanitizer, and it is 10x faster than HerbGrind, which is the state of the art. We could not run HerbGrind with long-running applications, but we could run FPSanitizer. Both of our tools are publicly available. Let me start by giving you some background on posits. Posit representation is defined by two parameters, n and es. N is the total number of bits and es is the maximum number of exponent bits. As the number of exponent bit increases, the dynamic range improves and precision is reduced. The first bit is used to store the sign of the number, 0 for positive, 1 for negative. The next set of bits is regime bits. Regime bits can be all 1 terminated by 0 or all 0 terminated by 1. Regime bits works as super exponent in posits. If any bits are left, then they are used to store exponent bits, which can be maximum of es number of bits. If any bits are still left, then they are used to store fractional bits. The number of bits used to store regime, exponent, and fractional bits changes based on the number that is being represented. More regime bits means less fractional bits, hence less accuracy, and that's how posits achieve tapered accuracy. One of the cool ways to understand posit number representation is by visualizing them as projective reals, with extremes as plus minus infinity and 0. Let's consider a 5-1 posit configuration. Here total number of bits is 5 and maximum number of exponent bits is 1. All the numbers which can be represented in this configuration are shown here with their bit strings. All other numbers have to be rounded to the closest value. Bit strings are color-coded with precision bits in black, exponent bits in blue, and regime bits in brown. Now I'm going to show you how numbers are distributed based on the number of precision bits in this configuration. Numbers close to 1, shown in the blue region, have maximum number of precision bits. Numbers in the green region have low number of precision bits in comparison to blue region. Numbers in the yellow region have lowest number of precision bits. This shows how precision changes based on the range of the number. Tapered accuracy is amazing because it provides more precision for certain numbers. However, it introduces additional challenges. Suppose you multiply two numbers in posits. The result can have lower precision than either of its operands. In contrast, floating point have fixed precision for all normal numbers. Now you write programs using posits and you encounter rounding errors. That's where PositDebug comes into the picture. In next few slides, I'm going to show you the approach behind PositDebug. We want to detect numerical errors with Posit applications. We achieve this goal by doing shadow execution with real numbers. We want PositDebug to be usable with long-running applications. Careful design of metadata and compiler instrumentation help us to achieve this goal by incurring lot less memory overheads in comparison to other approaches. We want developers to identify the root cause of numerical errors. To achieve this goal, we provide a directed acyclic graph of instructions to show the error propagation. The key contribution is how do we provide the DAG while maintaining constant amount of metadata with each memory location. Now let me show you how you can use PositDebug. We wanted to experiment with large existing floating point applications, but there was no Posit version of these applications. That's why we built AST to AST refactoring tool which automatically transforms floating point programs to Posit programs. Then you can use Clang compiler to convert this program to LLVM intermediate representation. Our LLVM pass instruments all the Posit computations to do the shadow execution in higher precision. Shadow execution is done in our runtime library. Now let me show you how you can use PositDebug with an example. I will walk through this example later on. Details of the program are not important at this moment. PositDebug is based on LLVM compiler instrumentation. Posit values can either be resident in registers or in memory. That means we need to store metadata for variables in registers and variables in memory. For variables in registers, we store metadata in the program stack. For variables in memory, we store metadata in shadow memory. Given the variable address, you can get the shadow address from which you can get the metadata. So what should we store in the metadata for variables in registers? To perform shadow execution, we want to store the real value, which is used to compute the error by comparing the real and posit value. We wanted to make PositDebug usable with long-running applications. Long-running applications often make call to the external libraries, which we might not be able to instrument. Such uninstrumented function calls might update the posit value. If this variable is accessed later on in the program, then shadow address of this variable can have a stale value. Hence, PositDebug can falsely report high rounding error. To resolve this issue, we store posit value so that we can reset the shadow value in such scenarios. Now suppose T4 has encountered significant rounding error, and we want to know how this error was propagated and amplified. To enable the user to diagnose the root cause of the numerical error, we store pointer to the metadata of both operands. Using these pointers, we can generate the tag of instructions to do the root cause analysis. Now the next question is, what should we store in metadata for variables in memory? The way program communicates with memory in LLVM IR is by storing the temporary to memory or loading the memory in temporary. All computations are done on temporaries. When we store temporary to memory, we store real value, posit value, and pointer to the temporary that is written to the memory. Storing pointer to the temporary helps us to trace the provenance of numerical errors within the memory. But there is one problem. What if the stack frame is deallocated? Then pointer to the temporary and shadow memory metadata is a dangling pointer. And we need to check if it is safe to access this pointer. That means we need to ensure temporal safety of all pointers in the metadata space. We use the idea of lock and key from sets proposed by Nagarkate et al. When the stack frame is allocated, it is given a new lock and key. Lock and key will match as long as stack frame is valid. Pointer accessing a stack frame inherits its lock and key. When the stack frame is deallocated, lock associated with the stack frame is invalidated. Hence, lock and key for the pointer accessing this stack frame won't match, and that implies it is unsafe to access this pointer. Now let me walk through the example step by step. For variables in memory, we store metadata in shadow memory. For simplicity, I'm just showing real value, posit value, and pointer to the temporary. For variables and registers, we store metadata in the program stack. The first thing I'm doing in this program is dereferencing a pointer ptr1. In shadow execution, I'm going to access shadow memory associated with ptr1 and load the real and posit value in the metadata space in foo's stack frame. To initialize the pointer to the metadata of A's operands, I need to access T28, which is the pointer to the temporary in the stack frame. If it is valid, then we copy metadata associated with the operands of T28. Otherwise, we initialize operands metadata to null. In this case, it is invalid, and that's why a pointer to the metadata of A's operands is set to null. Similarly, we load metadata for B from PTR2 and metadata for C from PTR3. Now I am calling root count function. For details on how do we handle function arguments and return, please see the paper. In root count, we are creating a new variable T1. In shadow execution, we create metadata for T1 in root count stack frame. We do real computation with real value of B and store it in T1's metadata. We store the posit value pointers to the T1's operands metadata, which is B in this case. We do the same thing for T2, T3, and T4. After computing T4, we notice that T4 has high rounding error. T4's computed value is totally different than the T4's real value. To diagnose the root cause of this error, we can traverse back following the pointers to operands metadata and investigate how the error was propagated. The first thing we have noticed that subtraction operation at T4 has error of 62 bits. That is, all bits are wrong. From T4, we can access the T1 and T3's metadata and notice that both of the operands have the error of 43 bits. We recursively traverse each node and construct the entire DAG, which help us to do the root cause analysis. We figure out that T1 and T3 have error due to loss of precision, and it is magnified in T4 due to catastrophic cancellation. Now we return from the root count function, and root count stack frame is deallocated. At this point, T5 metadata is storing a dangling pointer to T1 and T3's metadata. By checking temporal safety metadata, we can know it is unsafe to access these pointers. Hence, at this point, we won't be able to produce the DAG of instructions. The user has to put breakpoint just before this execution point to produce the DAG. This design of storing the constant amount of metadata in program stack and following it to get the DAG makes PositDebug scalable with long-running applications. Since PositDebug is based on compiler instrumentation, it can be used with interactive debuggers like GDB. As I mentioned before, the same ideas of PositDebug can be applied to debug numerical errors in floating point applications. And that's why we have built FPSanitizer. We have seen significant performance improvement because of the constant metadata design and compiler instrumentation. Paper has a lot of other details, and due to lack of time, I'm not going to talk about it. If you are interested, please see the paper. Now I'm going to tell you how we evaluated PositDebug and FPSanitizer. We wanted to address three main questions with our experiments. Does PositDebug detect numerical errors? Is debugging support useful? And does it work with long-running applications? To address the first question, we did experiments with a lot of micro benchmarks. Some of them were from Hub Grind Test Suite. We also tested with large spec benchmarks and our own codic math library. We detected a lot of numerical errors in all of these applications. To address the second question, I'm going to tell you a story. The motivation to build PositDebug was to help my group in building math libraries for posits based on codic method. It has a lot of numerical errors, and PositDebug helped in detecting and diagnosing the root cause of the errors. My group found PositDebug useful, and we improved the accuracy of codic library by 10x. The last question we want to address is the performance good enough. To evaluate this question, we took applications from Polybench and Spec and ran them with PositDebug. Our baseline is an application that uses the software version of Posits without any instrumentation. Since we are showing performance overheads, lower bars are better. For these experiments, we used 256 bits of precision for our shadow execution. Compared to the software version of Posits, PositDebug introduces 12x overhead on average. With the software version of Posits, PositDebug has low overheads and we found it to be useful. Now the question you might have is how much is the overhead with hardware version? Posit does not have hardware version yet. And that's why we compared with FPSanitizer, which is the floating point version. On average, overheads with FPSanitizer is 110x. In this evaluation, we are instrumenting all functions. But ideally, you want to instrument selective set of functions and overheads would be much lower. Before I conclude, let me give you a quick overview of related work. Since posits are very new, there is not much support for detecting numerical errors with posit applications. There are two closest pieces of work in floating point domain, that is HubGrind and FPDebug. Both of these tools are dynamic instrumentation tools based on Valgrind. HubGrind also produces DAG of instructions similar to our approach. But one of the things we observed that we could not run HubGrind with any of our performance applications. That's because HubGrind maintains metadata proportional to the dynamic trace of the program. In contrast, we store constant amount of metadata per memory location. To conclude, Posits is a new attractive representation for reals which provide tapered accuracy. PositDebug enables you to find numerical errors and debug them in Posit applications. The key idea is to keep metadata constant to the amount of memory usage of the program. It provides backtracing in the active set of functions to produce the DAG for root cause analysis. We have shown the same ideas are applicable for floating point applications. We believe both of these tools can help developers to detect and debug numerical errors effectively. Thank you for your attention. Please try it out and give us feedback.